Okay, I'm Michael Waterbury. I'm a senior here and I'm majoring in physics. I'll be graduating in spring. And the center of this talk is supposed to be about quantum spin systems, but I plan to also talk a lot about symmetry breaking and phase transitions and stuff of that sort. And I'm going to kind of start from ground one, so if you are familiar with quantum mechanics, you'll probably be a little bit bored for a while. I mean, it'll be a little short though, in that sense. So basically, initially what we're going to discuss is the postulates of quantum mechanics and what they mean and why they're important to quantum mechanics specifically. So initially, we propose that every state of a system, so you just imagine that we're describing something and we want to be able to characterize it. We're just going to generally characterize it by some vector, you know. So if we're talking about a vector in Euclidean space, we characterize it with its coordinates, x, y, z, etc. But it can go further than that. We can talk about what sort of spin it has, what sort of angular momentum it has, and what sort of energy the system has. And we're just going to generally define it as some vector psi. This is a notation in mathematics specifically, but it's also called a bracket in physics. It's Dirac notation. And basically what this corresponds to is a column vector, while the corresponding bra vector to this ket is a row vector. This is a normalized vector that exists in some Hilbert space. Normalized meaning that it has a probability of existing, so we're going to set it equal to 1. Since these represent probabilities, we don't want there to be a probability greater than 1, so normalized, these things have magnitude of 1. Next, we have that every observable has a Hermitian operator associated with it. Basically, all that means is that when we observe something, it's going to have a real value. We're not going to get anything imaginary out of it. And that's pretty straightforward if you think about it. We don't want to be observing something and thinking we should be getting imaginary value out of it, because what the heck is something going to be imaginary? We want to deal with real things. And one of the most important parts of quantum mechanics is the collapse of wave function. You've probably heard about that. And the idea is that if we measure something, it will collapse that state immediately. I'll talk about more of that in a little bit. And then the fourth one is just the Schrödinger equation, which just dictates how something changes in time. I'll write it down for the sake of it, but it's not that relevant for the talk. This is the Hamiltonian. It's basically the energy of the system, and it just says that the evolution of our state is dependent on the energy of it. That's basically all it says. Most of these are physically driven. Yeah, I mean, like, this is the only one that doesn't have an exact experiment that says that this is true, and we've just kind of accepted that this works for the most part. The Hilbert space is just kind of a nice feature of it. It makes sense for things to be able to do this, and then Hilbert space assumes linearity, which is really useful when we talk about superpositions of states and how we can operate on these states that have superpositions. Because if it's not linear, then, you know, if we have a state that we're just going to call something times a single state and then something times another state, this is a linear combination of two states. And so when we operate on this, we want to be able to operate it linearly. And that's all that the Hilbert space really says, apart from the fact that it also has an inner product, which is just this multiplication. All right. So now I want to talk about what it means for something to be quantized. So if you're familiar with quantum mechanics, you probably heard about the Stern-Gerlach experiments. Basically, we have something that we initialize in a state psi, and in Stern-Gerlach this associates with like an oven that's releasing particles of some state. And we want to observe this state, so we're going to use like a magnetic field along the z direction. Specifically, this has to have a gradient, just due to nature, and we're assuming that these particles have some magnetic moment associated with them that's going to cause them to get deflected outward. What we see in Stern-Gerlach and associated experiments is that basically, no matter the angular momentum of this state, we see that this shoots out in quantized parts. Basically, the distance between these is a set number, and there's a set number of beams. And the way that we characterize these is if there's a 0, you have a 0, and then you move 1, minus 1, etc. from that point, and this represents all of the states of our angular momentum. So in this case, we have our L equals 1, that's our total angular momentum, and our M state, which is a member of -1, 0, 1. Again, this is just something to generally state what our state is. This is just a statement about what our angular momentum is in this system. Something quite weird, particular to quantum mechanics, is the fact that this is actually the z component of L. And it's very particularly only the z component because the fact that, so if you study it, you'll find relations between angular momentum that are defined like this. And what this says is that these don't commute. And if you study quantum mechanics, you'll learn that that means they're not simultaneously diagonalizable, which basically comes to mean that we can't observe both of them at the same time. So in a sense, we can know the total angular momentum of this and a component of it, but not all three components, which is really important when we start to discuss how these things add together. And a physical realization of addition of angular momentum would be an interaction such that you have one particle with an angle with a magnetic moment causing a magnetic field operating on another particle's angular momentum. And this is realized if you have a Hamiltonian that operates like that. So this is the dot product between the two. If you study E and M, this is basically that interaction, where this magnetic moment is introducing a magnetic field that is interacting with this magnetic moment. And this is just the energy in the system described in our Hamiltonian. So this, I will write out for the sake of seeing it. And these two are, if we represent them on the basis of our original, is where this is a tensor product. I wouldn't worry about it too much. Basically, it just shows that we can consider these separately. We notice that these are in the basis of LZ, or SZ, and this is in the basis of SZ2, and that this is outside of the basis. So these vectors are not properly described. This operator here cannot properly be described in this state of the system. It is, in other words, it's non-diagonal. If you were to write out this operator in terms of a matrix, you'd see, let me make sure I don't mess this up. Yeah. This representation, which is very clearly non-diagonal because we have off-diagonal components. And now if we try to represent this in a basis of diagonal components, we find that we have basically vectors like this with eigenvectors, eigenvalues 1. We'll just go a little more like this. So this is a little weird, but this is basically showing, okay, so we understand how these operators here operate on these vectors. And this is representing these vectors in this basis. So what this vector is just, I'm just going to simply call this up vector or a down vector, where up represents up 1/2 and this represents down 1/2. And the same thing can be said for this one. So these states become up, up, down, down, up, down, down, up. And again, these are non-diagonal bases. So this is the vector up, up. This is the vector up, down. This is the vector down, up. And this is the vector down, down. And you can do the same thing across the vertical side, and you'll see that basically understanding how these operate, you get these values. So to continue, this vector becomes a superposition of two other vectors, where this is an eigenvector of this operator. So in the new basis, we cannot express it diagonally and straight up these vectors. If I were to operate on this vector, I don't get this vector back. And likewise, if I operate on that vector, I don't get that vector back. So this becomes up, down, up, and we get another vector with a separate eigenvalue of -3. So, and this is just a superposition with a minus sign between it. Alright, so this doesn't seem so crazy, but these are entangled states. These here. This is a realization of entanglement. Basically, if we were to observe the first particle and we see it in a state up, the second particle has to be in state down. And not only that, it's a superposition of two states, which is radically different from anything you'd ever see in classical mechanics. You could never see classically that one of these exists, or that it's a superposition of two states. Not only that, the fact that there's a transformation of information between the two particles that's instantaneous is also unheard of classically. And that's one of the key things that people try to test when they look at quantum mechanics, is this model real? How does this work out? And then this model works out beautifully. It predicts so many different things. So also we want to be able to express this more simply in another basis. So if we want to work on this in, say, another state that looks like this, since we understand how these things work, if we want to work on in another basis that looks like this with a total angular momentum, we'll say J, and we're going to give it angular momentum parts mj. And we want to know how these vectors correspond to these. So if we were to operate with J squared on it, we could figure out what the total angular momentum is, and if we operate with JZ, we can figure out what the angular momentum component is. I'm just going to skip that step because it's pretty trivial, but what you end up finding is that our new basis is formed out of what you can consider quasi-particles. So that first state here is down-down. This corresponds to 1, -1. The superposition of states corresponds with 1, 0. Corresponds to 1, 1, and the other system corresponds to 0, 0. Okay, so these are often referred to as singlets, valence bonds, Cooper pairs, all sorts of different things that this single entity will reflect on in upper level physics and really amazing phenomena that exist due to this fact. We also know that these things have lower energies due to the fact, well, they have different eigenvalues. These were all had energy 1, or an eigenvalue of 1, this had an eigenvalue of -3. So this has a lower value. So if this is the energy we're looking at, and J is a positive number, that means that this state would be preferred, just because it has a lower energy. And if you're familiar with stat mech, you know that lower energy states are preferred statistically over other states. Likewise, if we had this to be a negative sign, you'd see that these states are more preferred. Okay, so this interaction here of two angular momentum has many realizations in just atomic physics. What you see in atomic physics is if we have like, say, just an atom, and we want to describe its state. I'm going to ignore deriving the state just because it's well done in a lot of different physics, and, a lot of different classes, and it's online a lot. Basically, it has these energies with these states. And what this is, so if we're associating this with like the periodic table, this is, we have an energy 1, which is like hydrogen or helium, and you get an angular momentum and a momentum. But these states, because n is 1, have to be 0, because L has to be smaller than n, and m is dependent on L. So for like helium, you would have 1, 0, 0. And for hydrogen, you'd see 1, 0, 0. Where the spin of these then separates these two states. So this would have a spin associated with it, up or down. And then this is a superposition of two states, generally a singlet, but in an excited state it could become. So this is our system of a singlet. So this is when two particles have arranged themselves in an entangled pair to minimize the interaction of their two spins. So you see that this then gets that state because it's trying to minimize this interaction. And then we also see that because of this, right here, this is an anti-symmetric state. And so if you have two identical particles and they're fermions, due to the Pauli exclusionary principle, they cannot be in the same state. It's just impossible. It's just against physical law. And the way that that's described in terms of state functions is if we have some state of one particle and some state of another, and we want to swap the two particles, you get a minus sign. This is bad attention. So this corresponds to swapping the two particles, and then they're anti-symmetric by getting a minus sign. I didn't want to use wave functions, position wave functions. So just a way to, typically if you were to look at this, you'd see that they use this notation where they're using position wave functions. Where it represents that changing the coordinates of the two particles gives you a minus sign. But this is equal notation roughly, where you have a state of one particle, state of another one, and you switch the two states, you get a minus sign. Well, you see that this part here, our singlet state, satisfies that law. So the fermionic state of this is fully grasped by this anti-symmetry, and then the two states can be in the same wave function after that. Does that make sense? Okay, so this is the way that helium can have two electrons without having to go to an excited state. So if we didn't have this ability of spin systems and then to have opposite spins and fill the same position, then the helium would be a 2, 0, 0 state. But because these two particles cannot occupy the same positional state, the same NLM state here, the same energy state with angular momentums being equal, you see that now you have two full different elements that can exist in the same state, the same positional state. All right. So now that I talked about that, if we look at higher level systems, so more complicated atoms, where the angular momentum comes into play, and we have say something like that. I'm gonna erase a lot of stuff because there's a whole lot of clip here. We have our NLM states, and we have something in this state, we'll say, where it has an angular momentum of 1, a total angular momentum of 1. And we want to, all right, well, let's start this actually. All right, so we notice that our energy is only dependent on n, which means that these L and M's are degenerate in our system. Basically, it means that if we're looking at a system with two L and 1, this has possible states there, that one, where these all now have a degenerate energy. They all represent the same thing. But if we look at the system and it's, well, we see that this doesn't actually happen in atoms, clearly, because lithium and beryllium have different energies than boron, carbon, and nitrogen, and so on and so forth. So what's occurring is that these angular momentum are interacting within the system, whether it be with the nuclear spin, or the spin of the electron, or so on and so forth. So really what we lose is that we see that there's a lack of degeneracy between the two angular momentum due to the fact that the spin interacts with it. So we spin orbit splitting, described by, where this is the interaction of the spin of the electron with the angular momentum, and that causes splitting in this sense. So where we initially have our energy level, n equals 1, n equals 2, this now has a different amount of energy based on L equals 0, L equals 1. And if you know anything about basically how photons are emitted in atoms, when you have an electron in this state and it wants to decay down, it releases a photon with that amount of energy. So this creates the spectrum energy and the wavelengths that we see it in light. But now that these states have different energies, now we've created a new way for photons to be created, a new energy for these to be created, and we get more and more energies just out of single atoms that allow for these energies. And if we do this further, we can see that well, if we apply a magnetic field to this along the z-axis, now instead of, so these all in spin orbit, these all have the same energy. These are degenerate systems. But if we apply a magnetic field to it, now all of a sudden this has more energy than that one, and this has less energy than all of them. So we see that there's even more splitting, and we get an even more larger continuum of energies out of this. This, by the way, is known as the Zeeman effect, if you're familiar with it. And this occurs many, many, many times within atoms. So there's many different interactions you can consider and different transitions that could occur for a photon to be released. And so what we see is basically a continuum of energy from our eyes. So this is an amazing phenomenon if you think about it, because it explains why we see different colors, how these different colors are created. If you study astrophysics, this is how we understand what temperature things are in like the CMB and, not the CMB, the CMB is different. This is how we understand the temperature of the ISM, the interstellar medium, and when we think and how we study how stars collapse, and all sorts of these different phenomena that just exist because this can occur, because this splitting can happen, and we can see that this splitting is happening at certain times and certain temperatures. It's just amazing to me that this simple phenomena of additional angular momentum creates all these different states that we can then observe. That's just amazing to me. So I'm going to take a completely different turn. Instead of going to atomic physics, I'm going to kind of move to condensed matter. And kind of trying to take that to field theories and Bose-Einstein condensates and all sorts of cool things out of those quasi-particles I mentioned earlier. Okay, so if we think about some sort of hard condensed matter thing, and what's really happening for these things. So when things crystallize, they create lattices of particles. So we have a lattice of particles here. So what exactly causes these to have like magnetism, or what causes this system to rise? What sort of excitations do we see in this? Because if we have a certain amount, these things are set at a certain temperature or something of that nature, then clearly they're not going to be stable. They're going to be moving. They're going to be jiggling just by Brownian motion and not Brownian motion. Just thermal energy exists in this lattice, right? So if it's at a certain temperature, it can't just be set in stone still. So if we consider there to be some sort of motion in this, then that has to be associated with some sort of jiggling in this. But we know that this periodicity with this distance between them, this certain distance, we'll call it d. This is a distance d, and this is a distance d, and etc. And it's periodically, that's the minimum of it. So if we model this by a bunch of springs, basically we see there's a bunch of vibrations in these springs. Now if we consider this to be a quantum system, where you have the harmonic oscillator, we'll just write down 1 for a single spring. The Hamiltonian for a single spring. Where this is the distance between the two, and here's our oscillation frequency, and here's the momentum of it. If you're familiar with quantum mechanics, I'm just going to kind of do a hand wavy sort of argument here. This can be written in this form, where these are raising and lowering operators on the system. So this has, if we were to write the energy states of this, you see that's this, with energy states in. So we have a set number of states with certain energies associated with them with this. So this is associated with how fast an oscillator would be oscillating if this is higher or lower. And what these operators do is they would raise it or lower it. So this would basically create an oscillation on it. And if we were to write this out for n particles, so we take this to a new set of particles here with k particles. This is now the idea of this system, where we have a bunch of oscillations occurring. And we see that we can write this exact same thing out, and we get that this is a sum. Okay. All right. So these essentially are creating oscillations on the system. Now, the really, really cool thing is that if you study this system, you know that we call these oscillations phonons, and they're quasi-particles. What these operators do here is if we operate on the system, they create and annihilate these phonons. Which is a ridiculous amount of precision that you can have to talk about the system. The fact that you can look at this and say, there's particles in this universe of a field, basically. We're just considering this its own little system. And it's created a world where these particles can come into existence and fly away. And these physical realizations of this are the vibrations in this lattice. And so we have creation and annihilation of particles. This is second quantization. This is the stuff that you see in field theory, which is just ridiculous. Likewise, if we consider, this is just the momentum of it, right? And the Coulomb interaction between two atoms. But if we want to consider the magnetization of these particles and things like that, we have to consider how the spins are orienting on this lattice and things, and how these contribute. So if we then segue. Okay. Okay. So all sorts of different phenomena exist out of the fact that we have to orient spins on the system. So if these atoms are such that they don't have an even number of electrons, the electrons won't pair and create those spin zero states. And so then we have a net amount of spin on each of these atoms. And so we're trying to orient all of the spin on these atoms to minimize some interaction, and that's going to be the ground state of the system. So if you think about it, we wrote that interaction earlier between two systems, between the two. Now we're going to write it for some infinite number. So this is summing over all of the atoms and all these little spin interactions and how these things work. Well, we know how this minimizes, right? This is minimized into our singlet and our triplet states. where we had the up, down, minus, down, up, 1 over root 2 states. This is our singlet, this is our, what we called our lowest energy. So this was equivalent to our 0, 0 state. So if this right here is, we said positive, since this has an eigenvalue of -3, then our energy is minimized by creating as many of these singlets as we can on this lattice. So instead of these being definitely up or definitely down, these guys create a valence bond, and form these singlet states, or the valence bonds, or the dimers, there's a bunch of different names for them, and minimize this interaction between the two of them. So we have a bunch of different systems that are aligning, just kind of arbitrarily aligning. But the thing is that, what would cause a system for these two to pair rather than these two spins to pair? What is so radically different between the two? And the answer is that there's no different. These spins, the ground system is equally energetic for all of them, and they're fluid. They can just move around. So this state here, we have this, is also equivalent. These are exactly equivalent to, if we wanted to write this out, say this one's down, this one's up, this one's up, this one's down, this one's up, this one's down, etc. And we can pair them differently. Exactly equivalent systems. And so instead of there being a rigid ground state, we see that there can be a lot of fluidity in how this system aligns, and it's not exactly clear why it would pick one or the other. Okay, now this is all at really low temperatures, because at high temperatures, it's easy for these things to access those triplet states and basically align like that and not minimize the energy. Because temperature basically introduces a disorder to a system and makes it so that instead of it being in its ground state, maybe it's in its upper state, or it's because there's so many different particles in this system, basically temperature would dictate how many of these exist within our system instead of it being rigidly or fluidly in these dimers. And so so as temperature is introduced, we see these sorts of things, and so the net magnetization of these systems begins to come out. And so if we have two systems like this, then there's a net magnetic moment of the two, and it introduces some magnetic field to the system, and you can quickly reach, ferromagnets or anti-ferromagnets. So an anti-ferromagnet, basically you have all the spins disalign like this on our lattice, and a ferromagnet, you would have all of them aligned. Does that make sense? Yeah, okay, that's really simple. Okay. So, again though, we have this issue of why would it pick this state instead of, every spin being opposite? And this introduces a really cool idea of metastable states. So even though technically the eigenstate of this system would be it being half in that system and half in this system, we witness it in one of them. This is a root. We witness it in one of these two systems, right? So the way this is described is that, well, this is when we're in one of these systems, this is a metastable state with a certain lifetime to it. But it just so happens that if you do the calculation, antiferromagnets have lifetimes longer than the age of the universe. So these things, they're completely set in stone, but they're not even minimizing interaction. They're not like a real physical thing. There's something that exists because other things exist around them. If we didn't exist to see this, it would just be in this state forever. There would be no reason for this to align to this system or that system or whatever. So just by existing and observing things, we're changing the way that these things align, or we, not necessarily us, but other objects and these interactions break all sorts of symmetries in there and cause certain states to exist and be brought out in systems, which is just crazy the amount of arguments you can make just on the fact that there's a symmetry of this up and down that is broken by our observation. there's no reason for this state to be preferred over that state, but for whatever reason it is, and that reason keeps it in the state for longer than the existence of the universe. Now, that's just crazy profound to me. All right, so back to this stuff. So if we want to consider this being a lot of spins on a system, and we're interested in seeing the ground state, it can vary between systems. So if we're talking about the total interaction of this system, we have this, and then the interaction of between two of its states. This is a sum over all ensembles. Under some magnetic field. So this is our typical interaction between two, and this is basically the interaction between everything together. So this is like next nearest neighbor sort of interaction. So while these are interacting and it's dominant, these actually do interact, and so it's not necessarily so solid that it's going to go into this. Really, if we see this full sort of system where it's going to these states, you kind of see systems like this, where this is a distance d, and these form those singlet pairs like that, and so on and so forth. So even though I said that this is basically the ground state of the system, really, there's other interactions taking place into account, and it's not straight. So it's not as obvious as, oh, these are going to pair, these will pair, next nearest neighbors, et cetera, et cetera. There's a lot at varying circumstances where, maybe this particle wants to entangle with this particle, and so on and so forth. And you see crazy amounts of just intricacy and complexity in the issue, in the problem. It's not as straightforward as, oh, okay, these things are going to interact and they're going to go to the lowest state like that. There's a bunch of different things at play here, and that's kind of what this term is. So this is over the entire lattice what's happening. So there's been studies about, this is like for, here, so there's this is for looking at something similar to these molecules. You get Hamiltonians that look like this. And if we want to represent this in terms of the annihilation and creation operators that I was mentioning for like phonons, but this time it's for basically, instead of considering this as a bunch of we can consider this as a field of our singlet states. So basically we have a bunch of these states that are interacting as low as possible. We consider that to be our low energy or zero energy. And then excitations on this lattice would take into effect that, which is degenerate until we introduce a magnetic field, which we know will split into three different states. Okay, so that's what this magnetic field's doing, is it's causing the splitting. And we're just and this is really just two particles interacting that are fermions, but we're going to consider it with our model a field of a sea of these singlet states that can excite into this triplet state, which is then degenerate. So if you write this in, just to show you kind of what it looks like. you can write this in terms of accretion annihilation operators. So this is just our typical, so this is allowing these triplons to move across the lattice. So this is annihilating, creating them. And this is symbolizes the repulsion between if we put two triplons on top of each other. So if we were to put a triplon here and then triplon there, this is the repulsion that would feed this. Basically gives them angular momentum, so that these particles, instead of having to sit in one place, they have the energy to move here based on this. And this is just the interaction of the spin. So this is what gives us triplons. Right. And this right here is our magnetic field, and this is the interaction energy of the two. And what you see is if H approaches J, what happens is so if we plot our energy here, and this is our magnetic field, right, H. And we have our Zeeman state, so this is 0, 0. And then we have these states. And as the field increases, these separate. And what you see is that this state, or one of the two, depending if this is with or against it, finally reaches the energy such that these two have the same energy. And what happens when you have two degenerate states like that is you see Bose-Einstein condensates form out of these quasi-particles, these completely theoretical particles that we were introducing to model, have a physical realization in Bose-Einstein condensates of triplons in our system. That's just crazy. We're just completely hypothetical particles. These have no physical realization other than that they are a pair of two particles introduced in some sea of particles here with some magnetic field reaches a point where it transitions from being this excited, somewhat excited state here to just suddenly becoming a Bose-Einstein condensate. And this is what's called a quantum phase transition because it occurs at really low temperatures. So basically what a quantum phase transition is, if you understand what thermal phase transition, that's basically, so a thermal phase transition is when you move from like a liquid to a solid just based on the fact that it's releasing heat or something of that nature. But if we're looking at systems that are really low temperature, the quantum fluctuations within that system can dominate the temperature fluctuations. And we see that basically these quantum fluctuations between these two systems causes a phase transition when we reach a certain magnetic field. And this is causing Bose-Einstein condensates. That's so crazy. I don't know. And then I'll talk about superconductive theory for a little bit. Okay, so another thing is that the quantum phase transitions are they're basically, we don't even know what sort of physical systems this could lead to. I mean, we understand what like there's crazy realizations of what these ground states could look like given certain pushes and magnetic fields and quenching certain states and etc. It's just we have ideas and theories about the way things work. Like we have a triangular lattice which is dealing with frustration, and we're trying to put spins on it. And basically the question is, well, if this one's up and this one's down, what the heck does this spin do? Because it doesn't want to be up or down. And this is so basically the idea of quantum frustration. And then there's physical theories that predict that if we write out this Hamiltonian in this form, we get quasi-particles that exist in honeycomb lattices in between this guy. And just crazy intricate systems of crazy ridiculous things happening in these states that are all theoretically sound, and we're trying to show what's happening experimentally, and it's just a crazy intense amount of work that causes these. Another thing that we realize if we look at it in the system is, so if we're studying particle physics and we're looking at these systems and we're looking at Feynman diagrams. So Feynman diagrams are basically, you have a system and it's evolving into another system. So you have and then something happens here and then you have an exit. And well, the thing is that we don't really understand what happens here, but maybe this system does something like that instead. And what you do is you add up all of the different configurations that this could occur in, and you see that basically you get terms like these, and these with higher order, higher order, higher order. But the thing is that these terms come with a 1 over alpha in them every time you do it, and this alpha is big, so it's like 137 in this case. I think it's just alpha terms, because alpha is 1 over 137. And so this, and you see that this series converges. But if we're looking at a system like this alpha is the constant of our universe. But in the system of condensed matter, in our hard condensed matter system, our crystal, this is irrelevant. This isn't a system that we're looking at. These terms could have radically different values on them, and there's no need for this series to converge. And so what people like to think is that, well, basically we're looking at a hypothetical other universe, if we consider this system in this way, where we're not constrained to the physical constraints of our universe. It's just like a cool little thing that people like to think about in terms of, I mean, this is why this problem is really interesting to people. This is why people study theoretical hard condensed matter with quantum field theory. This is why people do this stuff, because it's really crazy. This term is so important in particle physics. It makes it so that, oh, well, you know, that like third order Feynman diagram, you know, it's kind of irrelevant in this case. But in this case, there's no reason for that term to go away. We have to just experimentally view it. It's just a crazy realization of what could happen if, let's say alpha's 10 in another universe. And then that universe could possibly have twins that look like some crazy thing that just creates particles that do other crazy things. I don't know, it's pretty profound to think that we could be viewing what could hypothetically be another universe when we look at these systems. That's just a crazy, crazy, crazy thing that I think is just miraculous about the systems. All right, yeah, so I was going to talk about condensed matter, or superconductors. So superconductors are like really, really crazy. I'll just talk about quantity actually. Okay, so the theory of superconductors, BCS theory, I'm not too familiar about, but I think it's really cool, so I'll tell you what I know about it. So this BCS stands for Bardeen, Cooper, and okay. So the idea with BCS theory is they realized that when they're looking at a lattice like this, there's an electron and there's a hole in this set, and basically these holes are gonna attract each other. But there's like, in order for that to occur, these systems have to entangle with phonons in the lattice, and then form Cooper pairs with each other that then can move along in the system superfluidly, like superconducting, so that there's no resistance, and et cetera. And that's just, again, a physical realization of these quasi-particles here, these Cooper pairs that we have physical meaning, is just completely ridiculous. Like if you study, if you're an undergraduate, when you study electrodynamics, you'll find out that electric fields, they're not just a tool. They have physical realizations. They have angular momentum associated with them. Then, basically we don't have conservation of angular momentum or energy without realizing these fields have real physical realizations. Like you without the field there, like the electric field, you don't understand the system. Our physics breaks down. The fields are real. Like that's such a crazy thing. when I learned that, my mind blew up. I don't know. Yeah, so BCS theory is pretty cool. It gets the same sort of field theory look to it, where you have creation annihilation operators, and you give it, you know, how this was representing the angular momentum of being able to move from one lattice point to another. You have that sort of term in it, and this derivation is crazy in my mind. Like I don't even know where to start on deriving this. I can probably derive this Hamiltonian, but going to that is another level. I'm not there yet. So, yeah, I guess that's my talk. Is anything you want to know about, hear about, didn't want to follow, want me to re-explain? All right, guess not.